بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. نبدأ اليوم بأول محاضرة أونلاين في مادة Power System Reliability. كما تعلمون لقد وصلنا عند طريقة ما يسمى Frequency and Duration Method. Okay. Frequency and Duration Method. As we state, this method evaluates the adequacy of static generating capacity. It consists of three models, like the loss of load expectation method, or like the loss of energy expectation method. One, a generation model. Two, a load model. Three, a risk model. So we are going to start with the generation model. When we finish, we select a load model. Then we can combine the two to produce a risk model. A risk model, this will give the duration and frequency of a given capacity outage. So now we're going to start with the generation model. Okay. Okay, generation model. I'm going to revise the concept of a frequency as we have seen in the two-state model. We have on, we have off, and we can move from on to off by the failure rate lambda, and from off to on by the repair lambda mu. Here we have the availability A, here we have the unavailability U. As we said, that the frequency of occurrence of A, frequency of on, is the probability of being on times the rate of departure from on, which is lambda, and the frequency of off state with the probability of the off, which is U, and times departure rate, which is mu. Okay? So therefore, this definition of frequency of being in a given state times the rate of departure from that state. Okay? So therefore, hence, for a given generating system, one has to find all possible states of this system. This will be illustrated by the following generating system as an example. Okay, let's now start with our example. Okay, example. في عندنا اليونت نمبر، في عندنا الكاباسيتي الميجا وات، then عندنا اللامدا failure per year، then we have mu repair per year. We have unit 1, 2, and 3. Capacity 25, 25, and 50. And failure rate, it is 0.01, 0.01, and 0.01. And we have the repair rate 0.49, 0.49, and 0.49. Therefore, availability equal mu على lambda plus mu, which is equal to 0.49 on 0.5, which is equal to 0.98. إذن mu equal 1 minus A equal to 0.02. So therefore, the generating system will be represented by two approaches. The first one, a table which illustrates all possible states, and the second one, the so-called the state transition diagram. We'll start with the possible states of all these units. As we have explained before, that the number of states equal 2 to the power n, where n is the number of units. In our case, we have 3 units. Hence, the number of states equal 2 to 3, which is equal 8. So in our case, we have 8 states for this 3-unit system. And this is the following table. All right. Here we have state number. Okay. We have 1, 2, 3, 4, 5, 6, 7, 8. Hence, a unit 1. Here we have unit 2, and here we have unit 3. And capacity out here. Then we can have all the units are up, 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 up. Or just to be clear, just let's be clear. on, on, on. The capacity out, 0 megawatt. Here we have off, on, on. And we have 25 megawatt. And we have on, off, and on. And for the 3, we have 25 megawatt. For state 4, we have on, off. Then we have 50 megawatt out. And for state 5, we have off, and we have here on. Then we have 50 megawatt. And for state 6, we have off, we have on, we have off. Then we have 75 megawatt. State 7, we have on, we have off, we have off. Then we have 75 megawatt. And the last state is all off, off. And we have 100 megawatt out. Well, on, the unit is working, and off, the unit is what? Down. Okay? All right, now we can start with transition diagram. Okay, now we start with the second approach, the so-called the state transition diagram, as follows. So here we have the state transition diagram. Here, each state is represented by a block, as follows. So, we have here state 1. Then, here, we have state 2. Here, we have state 3. And here, we have state 4. And here, we have 5. Here, we have 1, 2, 3, 4. Then we have 5. Then 6. Then 7. Then 8. All right. Now, we have to know the following convention, that we can move from one state to another only by what? By one transition. So, let's go to state 1. As explained in the table, the 3 units, they are on. Now, I can move on from state 1 to state 2. That is when unit 1 has failed. It means that is I have here lambda 1. Now I can move from state 2 to state 1 by repairing unit 1. Therefore I have here mu 1. Please differentiate between mu for the repair rate and u for the unavailability of the unit. By similar approach, I can move from state 1 to state 4 by the failure of unit رقم 3. So therefore I have here lambda 3. I can go back by the repair rate by mu 3. Now I can move from state 1 to state 3 when we have unit 2 has failed. Therefore I can go here lambda 2. Then I can go back to U1 by the repair rate mu1. And so on, we can have the following transition rates. I can go from 2 to 5, by lambda 2 and go back by mu 2. All right. Then I can go from state 5 to state 3 by repair rate of mu 1 and here by lambda 1. Okay. Then I can go from state 2, okay, state 2 to state number 6 as follows. All right. All right. So, therefore, so just to make correction, this is number 7 and this is number 6. Sorry about that. Okay. So here I have mu 3 and here I have lambda 3. Okay. And so on. So therefore, I can go and from here by mu 1 and here lambda 1. All right. 7, I can go up here from 7 to 3 by mu 3 and this is lambda 3. Okay. And then I can go from state 5 to state 8 by lambda 3 and this is mu 3 and here I can go 8 to 6 by mu 2 and here by lambda 2 and from 8 to 7 I can go by a repair rate mu 1 and this is lambda 1. Okay, so I can go also from 6, from 5 to 3. This is 1. All right, so these are the transition rates. Just please note there is no transition between 2 and 3. Why? Because here is only 1 is available. Because in 2 was, here in 2 was 1 off, with 2 on, with 3 on. In 3, it was 1 on and 2 down and 3 up. Okay, so 1 off I should on one transition, with 2 on, 2 down, so we are not allowed for 2 transitions, only 1 transition is available. So therefore, this is the state transition diagram. Now we are going to evaluate the duration model. It consists of what? The capacity on, transition rates, and the frequency. Note, for example, I'm going to see that is the frequency of occurrence of state 1 is equal to what? Probability of being in 1 times age is sum of the transition rate, which is lambda 1 z lambda 3. Okay, now we'll carry on the next slide. Now I'm going to give an illustration, an example, how to calculate the probability and the frequency of each state. For example, let us consider state number 2. We say now, illustration, for calculating probability and frequency of each state. For example, consider state number 2, where unit 1 down, unit 2 on, unit 3 on. إذا probability of state number 2 is equal to P1 off times P2 on times P3 on, which is equal to 0.02 times 0.98 times 0.98, and this is equal to 0.019208. Hence, frequency of state 2, F2, equal to probability of state number 2 times the sum of transition rates. 2 is equal to 0.019208 times mu1 plus lambda 3 plus lambda 2, which is equal to 0.01928, 0.49 plus 0.01 and plus 0.01, and this will be equal to what? 0.00979,608. So this is the procedure which we can do to calculate the power and the frequency of each state. Therefore, by applying the same procedure for the other states, the following tables can be found. So we can put here the state number. We put here capacity out, of course, in megawatt. Here, individual probability. On we put the state frequency. F. So we have states 1, 2, 3, 4, 5, 6, 7, 8. Here we have 0, we have 25, we have 25, we have 50, we have 50, and we have 75, and we have 75, and we have 100 mega up. Probability, we have here 0.941192, we have 0.019208, we have 0.019208, and we have 0.1928, and we have 0.00392. For the 75, we have 0.00392, and we have 0.00392, and finally we have 0.0000008. Okay. All right. And now the frequency F is equal to 0.02823.576. We have 0.0097608, and we can leave the rest for you to evaluate them by using the state space diagram. If we carry on, we can find the frequency at the end here is equal to 0.0001176. So in our case, we can have this the so-called the generation model, because it's a fact of the capacity out and it is a probability. Up to here, you can find this is the model used for the loss of load expectation and the loss of energy expectation. But what did you think now we added? We had this column which gives the frequency of occurrence of each capacity on outage. That's what we said. For example, if we talk about state number 2, for a capacity of 25 megawatt, what's the frequency of occurrence? It is 0.00978. This is giving us the occurrence per day. This is the occurrence per day. What does it say? For this system, for example, I can have megawatt out for this frequency 0.00001 occurrence per day. Now, what you can observe, we can have in this table identical frequencies. For example, 25-25, 50-50, and 75. So what we're going to do now, we are going to merge the identical states. I'm going to merge 25 and the 50 and the 75 into a single state. Okay, now as we said, we are going to merge the identical states into an identical state. First, we say that the previous table shows identical states of capacity. For example, states 2 and 3 have capacity of 25, and states 4 and 5 have capacity of 50 megawatt, and states 6 and 7 have capacity of 75 megawatt. So therefore, each two identical states have to combine into a single state. As we show now. نقول hence each two identical states have to be combined into or merged into a single state by using the following subscript. I refers to identical states. K refers to the merged state. So now we are going to show these equations which are going to be used. Now we are going to show the equations or expressions which can be used to combine the identical states as follows. We say the capacity outage of state K equal CK, C1, C2 until Ci. The probability of state K is equal to Pk, which is equal summation of Pi and the frequency of state K is equal to Fk, which is equal the sum of Fi and the transition rate the transition rate of state K equal to lambda plus lambda I should be subscript. Plus minus K, the plus departure for an upper state, the minus for a lower state, which is equal to a summation of Pi times lambda plus I over Pk. So now by using these expressions and equations, we're going to find the following capacity outage table with frequency. So, having applied the previous expression and equations, the following reduced generation model will be obtained. So therefore, the reduced generation model will be as follows. So now we can find that the 8 states has been reduced into 5 states. So we have here the state number, here the capacity out in megawatt, here we have the probability Pk, and we have frequency Fk. So we have state 1, 2, 3, 4, 5. So we have 0, 25, 50, 75, and 100. All right. Here we have 0.941192. Here we have 0.038416, and here we have 0.01960, and here we have 0.000784, and here we have 0.0000248, and the frequency here we have 0.02823576. We have 0.01959216. We have 0.01018 and we have 0.0077616, and we have 0.0001176. So that is what we have for today's lecture. We have found the generation model, actual states, emergent states, and we have ما يسمى الفريكونسي column. So we can consist of the state number, the capacity out, also we can calculate the capacity in, and the individual frequency for each state, and the frequency of each state. Once again, to illustrate the case, frequency, it means what is the frequency of occurrence per day for a given capacity outage. So next lecture, we're going to talk about how we can calculate the cumulative frequency and cumulative probability. Thank you very much.